So, have you completed? So here the idea is simple. If we have sufficient energy, then there will be an emission. If the energy is less, there won't be emission. Okay. So if you write that one as a note, the electrons emitted from the metal surface is called photoelectrons. Okay. Due to that light, UV light, the electrons emitted, we call them as photoelectrons. Always remember the energy of a single photon, the energy of a single photon only can be used by a single electron. Okay, it cannot be shared among electrons. That's important. The energy of a single photon cannot be shared among the electrons. Third, when a photon contains energy which is less than the energy required to remove the outermost electron, the photon will reflect without energy without any energy losses. So that is also clear. We just discussed now. Note these three under note. Okay, done. Okay, next let's look at the laws of photoelectric emission. Laws of photoelectric emission. First, let us understand that in simple. After we can note it down. Okay. Now, let's say on a surface, there is a photon. The intensity of photon. In this example, let's consider there is 10 photons every second. Then how many photons will be, how many electrons, how many photoelectrons can be released? Now let's say these have sufficient energy, okay? They are with sufficient energy. So these can release 10 electrons. These can release 10 electrons. We only have, our intensity is only 5 photons per second. 5 photons per second. Then it will release only 5 electrons per second. So let's say this is E1. The energy of this photon is E1. This is also E1. and E1 is greater than E dash. E1 is greater than E dash. Again, we have the same metal surface, and this time we incident photon of energy E2, at the same intensity, 10 photon per second. And here also it's the same surface again, and we incident photon of energy E2, 5 photons per second, Now, E2 is greater than E1. What's your idea about the number of photoelectric electrons released in the first case and in the second case? Do you have any idea? How many photons might release in the first case and in the second case? So, no idea. Okay, here 10 electrons will get released, and here 5 electrons will get released. So what's the reason? Now, the energy of a single photon, it can only release 1 electron. Okay, and the condition has to be the energy of this should be greater than the energy required. And in the second case, again, we have 10 photon per second. So in a second, it can only release 10 electron because E2 is greater than E dash. What will be the difference? What will be the difference between these two cases? The difference is this energy. The energy of this photon will be used for two purposes. The first one is to release that electron. Second one is the kinetic energy of that electron. So, in case of E2, the energy required is same, but kinetic energy will be high. Is that idea clear? So here it will be 5 electrons. Are you all clear, or should I explain once again? Saja and Shahama, did you get the idea? Okay. Now only let's look at these two. Let's compare these two cases. Now, what can you tell about their intensities? Are their intensities same or different? Here we have 10 photon per second. Here also we have 10 photon per second. Therefore, the intensities are equal. Okay, the first point. The second point, E1 is greater than E dash, and E2 is also greater than E dash. Therefore, there will be photoelectric electrons. Photoelectrons is present. And they mention that E1 is less than E2. E1 is less than E2. We wrote a note, right? One photon can release only one electron. Therefore, in 1 second, we only have 10 photons. Then it can release only 10 electrons. Here also, we have 10 photons. That means it can only release 10 electrons. But there is a difference in the energy, right? Here the energy is E1, here the energy is E2. So, these energies used to remove the electron plus for the kinetic energy of the electron. As it is the same metal surface, the energy required to remove is same. That means if these two are same and E2 is greater than E1, this kinetic energy has to be greater, right? Is that idea clear? So, now tell me, photoelectric emission. Photoelectric emission, does it depend on intensity? I mean the number of photoelectric emission. Does it depend on the intensity? Yes. Does it depend on the frequency? No, as far as it is greater than the uh, required frequency. Okay. Now look, number of photoelectrons. Okay. Number of photoelectrons. Does it depend on frequency? No. Are you clear with these 2 points? Look here, the intensity is greater. The intensity of E2 is greater than the intensity of E1. Sorry, not the intensity, frequency, okay? Frequency of E2 is greater than the frequency of E1. Still, the same amount of electrons is released. Clear with these points, right? Saja? Okay. So, under laws of photoelectric emission, let's note this. Mhm. Not this one. First note. Look, the number of photoelectrons emitted per unit time is directly proportional to the intensity. Copy the second one also. As the frequency of radiation increases, the maximum kinetic energy increases. once you copy the second one, here within brackets, we have a statement, right? Write that one also and tell me if you are clear, if you understood what that statement means. Okay, once you have copied the second one, go through this statement and let me know if you understood it. Okay. Why this is 45 degrees? The reason is when you have one photon, it will release only one electron. Two photon, two electron. Okay. So done. Shahama, did you understand this statement? Kinetic energy is independent of intensity of radiation. Now look that statement. Now I took two examples, right? In the first one, we had 10 photons per second. And in the second one, we had 5 photon per second. 5 photon per second. Now let's say in both the cases, I shine the surface with the same radiation. Then here, the number of photons released will be 10. Here, the number of photons released will be 5. What can you tell about the kinetic energy maximum? Are they same or different? Now we are looking about the kinetic energy of a single electron, right? Single photon releases a single electron. So we are talking about the kinetic energy of that electron. Just because there are 10 electrons being released, will that change the maximum kinetic energy of a single electron? No, right? So the kinetic energy maximum is independent of intensity. It is independent, but dependent on frequency. Both of you are clear with that point? Shahama? So look at the next point. No emission occurs until incident radiation has reached the minimum required frequency. Okay. So when it comes to the required frequency, let's say required frequency is E naught. That means it has only energy. This radiation has only energy to emit the electron, and there is no kinetic energy. The kinetic energy is 0. So that is marked here, F naught. And when we increase the radiation, when we increase the frequency of the radiation, now the energy required, to remove that electron remains the same, but kinetic energy only will increase. So if we plot this in a graph, we get a graph like this. The graph between kinetic energy maximum and frequency will look like this. Note the third one. I hope both of you are okay with that. So this minimum frequency, we call it as the threshold frequency. And the minimum energy required, we call it as the work function. Just now I wrote E naught, that is the work function. So note them also. You have noted, let me know. Note this also. So we use the symbol phi. We use the symbol phi to show the work function. We use the symbol phi to show the work function. So phi is equal h f naught. Completed. Then we have the equation for threshold wavelength. So that is the maximum wavelength required for a photoelectric emission. Because when the wavelength increase, when the wavelength increase, what happens to the energy of that photon? It will decrease. So we look for the maximum wavelength. For the maximum wavelength, that means we are talking about the E naught, the minimum energy required. Okay. So note this down and look, the work function, F naught and lambda naught, all of them depend on the material only. So depending on the material, some materials might need a lot of energy. Some material might need less energy. That means we are talking about the work function. So the work function depends on F naught, or it depends, sorry, F naught depends on work function. F naught depends on work function, or lambda naught depends on work function. It's obvious, right? So note it down also. Come on, note this one also. Once you have completed, let me know. I said here lambda, when lambda increases, E naught decreases. Therefore, when we say threshold wavelength, we look for the maximum lambda, then only we get the minimum energy required to remove an electron. So maximum wavelength. Okay. uh, so here we know that work function obviously depends on the material. So this work function, depending on the work function, we can find F naught or lambda naught. Okay. So all of these work function, F naught and lambda naught, all of them depend on the material only. I hope Shama, you're okay with the idea. When you're completed, let me know. Okay, next, let's discuss about the photoelectric cell. Here, again, it's the same idea. Now, we are going to prove that uh, what will happen to the photoelectric emission when we increase the voltage or when we decrease the voltage, and during the same intensity, different frequencies. So that is what we are going to discuss. Okay. So next topic, the photoelectric cell. So again, I will explain what's happening in the photoelectric cell. So this photoelectric cell, this is an experiment to prove this photoelectric emission. Photoelectric cell. So here, this is the experimental setup. Now here we have microammeter, and in this setup, this is the cathode, and this is the anode. This setup actually looks something like this, a bulb-like structure, which is tall, and we have a C-shaped foil, and over here we have this rod. Okay, when we look from above, this is how it looks. So this is not actually a small C-shaped thing, it's a half cylinder like. So that's the cathode here. What we do here is we shine light, or we radiate this cathode with electromagnetic wave. We radiate this cathode with electromagnetic wave. During that, if the energy of this electromagnetic wave is sufficient, it will release photoelectrons. It will release photoelectrons. And these photoelectrons will be captured by this anode and it will flow in this circuit. So we must be able to take a reading. A reading should be observable if this is true. Okay, so that's the experiment in simple. So draw the experimental setup. Under this, write these 2 points. When light is made to fall on the cathode of the photoelectric cell, photocurrent is produced. So this current we call as the photocurrent, okay? When electrons flow in the circuit, it's photocurrent. When electrons flow, that means we have current in the opposite direction. We have current in the opposite direction, and that current we call as the photocurrent, because this current is produced when light is incident on this surface. Once you have completed, let me know. Sajadan. Okay, next put on the topic, demonstration of photoelectric effect. Demonstration of photoelectric effect using photoelectric cell. Using photoelectric cell. We have a similar setup. This time we are connecting a voltmeter to measure the voltage across this, and we have a microammeter to measure the current, and then we have an additional setup to provide an external voltage. To provide an external voltage, we also have a variable resistor. So this is a sliding key. Using this sliding key, we can adjust the voltage. 1 minute. So using the sliding key, we can adjust the supply, right? We can adjust the supply voltage. So this is the sliding key. And we have a voltage supply. Again, this is the cathode, anode, and electromagnetic radiation. And photoelectrons. The meeting might end.